Assalamualaikum and a very good morning. Okay, these are the outlines for today's lecture. So we are going to look at the electromagnetic spectrum, in which the principle of wireless communication is transmitting and recepting an electromagnetic wave. And next, we are going to look at the definition of what is the antenna and how the antenna radiates, and lastly, different types of antennas. Okay, the slide shows the electromagnetic spectrum. As mentioned earlier, the wireless communication principle is based on the transmission and reception of electromagnetic wave, and the electromagnetic wave or EM wave can be characterized by different frequency and wavelength lambda. Okay, so lambda is given by c over f, in which c is the speed of light and f is the frequency of interest or the application frequency. Right, so based on the spectrum, different frequency range may having different types of EMF sources. Okay, we can see that as the frequency increases, so the wavelength gets smaller. Okay, you can see this wavelength gets smaller. So the wavelength for one cycle, this is your T, and you can get your F. And from this, you can calculate the wavelength in lambda. All right, so when the frequency increases, the wavelength gets smaller and the energy of the signal getting better, and the signal can penetrate better at higher frequency than lower frequency. So as antenna designer, so you need to consider designing an antenna based on the specification at specific frequency range. Okay, at lower frequency, it is called radio wave, and the frequency range is from 3 kilohertz to 300 megahertz. And from 300 megahertz to 300 gigahertz, it is called microwave spectrum. And higher frequency range from 30 gigahertz up to 300 gigahertz, it is called millimeter wave. Slide summarizes the EMF guidelines by different regulation bodies. Okay, different country may refer to a different set of standards. Okay, this is to ensure that the antenna designs lies or fulfill the required safety limits. And for Malaysia, we have MCMC that regulates all matters related to communication and multimedia, including the spectrum. Right, the table on the right hand side shows different types of application depending on the frequency range. So what is an antenna? So it's an electrical device which converts electric power into radio waves prior transmission, and vice versa, meaning that at the receiving end, the radio waves will be reconverted back into its original signal for reception. So it is usually used with a radio transmitter or receiver, and antenna can also be thought as a transitional structure between free space and guiding device. Okay, guiding device may be free space or guided device such as the waveguide. So by using an antenna, we can perform daily activities such as mobile communication, and then watching television. We can also listening to online streaming or radio streaming. Let's recall the communication system, which consists of three main components, which are the transmitter. Okay, so at the transmitter, the electrical signal will be converted into the electromagnetic wave form. So the signal then will be sent or will be transmitted over a transmission medium. Okay, either it is a free space or guided transmission medium, such as waveguide or fiber optic cables, and then it will be sent to the receiving end. So at the receiver, okay, the electromagnetic wave will be reconverted back into the voltage signal, and demodulation process takes place, and the end user or the end recipient will be receiving the signal as similar as the one transmitted at the transmitter. Okay, so this illustrate the figure illustrates the relation between the transmitter and the receiver, in which we have the medium in between that will transfer the transmitted signal to the receiver, and on the other hand will be receiving the signal from one end and retransmit it back to the other end. Okay, let's look at how the overall communication system works from the transmitting end to the receiving end.
At the transmitting end, it converts electrical energy into electromagnetic waves and then radiates into free space. At the receiving end, it receives electromagnetic waves and then transforms them into electrical signal, which acts as input for receiver.
Okay, let's spend a few minutes to look at how the electrical signal at the transmitter is converted into electromagnetic waves, which consists of electric and magnetic fields prior transmission over a transmission medium.
We have an electric signal, so how do we convert it to an electromagnetic wave? You might have a simple answer in your mind. That is, to use a closed conductor, and with the help of the principle of electromagnetic induction, you will be able to produce a fluctuating magnetic field and an electric field around it. However, this fluctuating field around the source is of no use in transmitting signals. The electromagnetic field here does not propagate. Instead, it just fluctuates around the source. In an antenna, the electromagnetic waves need to be separated from the source, and they should propagate. Before looking at how an antenna is made, let's understand the physics behind the wave separation. Consider one positive and one negative charge placed a distance apart. This arrangement is known as a dipole, and they obviously produce an electric field as shown. Now, assume that these charges are oscillating as shown. At the midpoint of their path, the velocity will be at the maximum, and at the ends of their paths, the velocity will be zero. The charged particles undergo continuous acceleration and deceleration due to this velocity variation. The challenge now is to find out how the electric field varies due to this movement. Let's concentrate on only one electric field line. The wavefront formed at time 0 expands and is deformed as shown after 1/8 of a time period. This is surprising. You might have expected a simple electric field as shown at this location. Why has the electric field stretched and formed a field like this? This is because the accelerating or decelerating charges produce an electric field with some memory effects. The old electric field does not easily adjust to the new condition. We need to spend some time to understand this memory effect of the electric field, or kink generation, of accelerating or decelerating charges. We will discuss this interesting topic in more detail in a separate video. If we continue our analysis in the same manner, we can see that at 1/4 of a time period, the wavefront ends meet at a single point. After this, the separation and propagation of the wavefront happens. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. If you draw electric field intensity variation with the distance, you can see that the wave propagation is sinusoidal in nature. It is interesting to note that the wavelength of the propagation so produced is exactly double that of the length of the dipole. We will come back to this point later. This is exactly what we need in an antenna. In short, we can make an antenna if we can make an arrangement for oscillating the positive and negative charges. In practice, the production of such an oscillating charge is very easy. Take a conducting rod with a bend in its center and apply a voltage signal at the center. Assume this is the signal you have applied, a time-varying voltage signal. Consider the case at time 0. Due to the effect of the voltage, the electrons will be displaced from the right of the dipole and will be accumulated on the left. This means the other end, which has lost electrons, automatically becomes positively charged. This arrangement has created the same effect as the previous dipole charge case, that is, positive and negative charges at the end of a wire. With the variation of voltage with time, the positive and negative charges will shuttle to and fro. The simple dipole antenna also produces the same phenomenon we saw in the previous section, and wave propagation occurs. We have now seen how the antenna works as a transmitter. The frequency of the transmitted signal will be the same as the frequency of the applied voltage signal. Since the propagation travels at the speed of light, we can easily calculate the wavelength of the propagation. For perfect transmission, the length of the antenna should be half of the wavelength. The operation of the antenna is reversible, and it can work as a receiver if a propagating electromagnetic field hits it. Let's see this phenomenon in detail. Take the same antenna again and apply an electric field. At this instant, the electrons will accumulate at one end of the rod. This is the same as an electric dipole. As the applied electric field varies, the positive and negative charges accumulate at the other ends. The varying charge accumulation means a varying electric voltage signal is produced at the center of the antenna. This voltage signal is the output when the antenna works as a receiver. The frequency of the output voltage signal is the same as the frequency of the receiving EM wave. It is clear from the electric field configuration that for perfect reception, the size of the antenna should be half of the wavelength. In all these discussions, we have seen that the antenna is an open circuit.
Thank you.